session will be moderated by Dr. Nadishani. So Dr. Nadishani Nanakara, Senior Lecturer, Department of Civil and Environmental Engineering, University of Peradeniya. She have earned her PhD from National University of Singapore and focused on physiochemical water and wastewater treatment methods. I cordially invite Dr. Nadishani to moderate the session.
Okay, thank you, Dr. Gayan. Now it is the time to begin the webinar. Now today's webinar topic is Brackish and Seawater Desalination, reverse osmosis and other technologies. Now today we have two distinguished speakers with us. Let me introduce the first speaker of the day. Okay. Associate Professor Ling Hua Fan. Now, Prof. Fan is affiliated to the School of Engineering, RMIT University, Australia. He is an expert in water quality and management, drinking water and wastewater treatment, wastewater reclamation, membrane technology, advanced oxidation processes, waste minimization, and resource recovery. Now, today, Prof. Fan will deliver his talk on desalination in Australia, an overview. Over to you, Prof. Fan.
Okay. Okay. Can everyone see my screen?
Yes, we can see your screen.
Yeah. Thanks for the introduction, Dr. Yakra, if I pronounce the correctly. I don't know, hopefully. I'd like to thank the organizers for the invitation. And in my talk is pretty much a high-level overview of the desalination in Australia. So I'm going to talk a bit of the journey of Australia in the desalination. I will talk about the key drivers behind the decisions to build the major seawater desalination plants. And then I will talk about the issues and challenges facing the industry. And then, of course, opportunities and also what important lessons we have learned from this journey. I'm sure Professor Wang will cover more on the technical sides of desalination in her talk a little bit later, particularly in the innovative membranes for desalination and water reuse. It looks like a good combination. We know desalination is a very attractive approach to address water scarcities because it provides a new source of water to meet the critical needs of human beings and also the economic development. It is also a good way to against the effect of climate change and the growing populations and drought, because basically seawater is endless. We could use as much as we can and at any time. A little bit history about desalination. So in Australia, people use wood-fired distillations for providing drinking waters. For example, in Western Australia, the distillation equipment were used to produce drinkable waters for the miners for the gold fields in Western Australia. So that was over 100 years ago. So this sort of thing has been used like this. This is basically a thermal method, use this distillation. And we have seen the larger scale thermal or distillation methods. The first plants, large plants in the 1950s, built to produce drinkable water. And we have also seen those first commercial plants in the 1960s and 1970s for the desalinating the brackish water and the seawater. And this actually laid the foundation for today's desalination industry. As you can see globally, the growth of desalination is very, very rapid. As you can see from the 1960s and 70s, the capacity and number of plants are not very many or not very much. But today, as you can see, we have nearly 20,000 desalination plants around the world, with about 80% of them are in operation. And Australia have been riding the trend. Most of the major seawater desalination plants in Australia were constructed and completed during 2005 and 2015. So as we can see, this is an exponential trend showing that desalination is becoming a attractive and also practical way to produce fresh water. So like many other countries, the key drivers of the desalination in Australia is actually the drought. Over 1997 to 2010, Australia in many parts experienced the longest drought over its history since 1901. So this drought was so serious, right? It had big impact to many aspects of people's life in Australia. And this drought has been termed as Australia Millennium Drought. Apart from that, the rapid population growth has also put extra pressures to the governments to secure water supplies. For example, in Melbourne, over the last 10 years, so the population increased from 3.8 million to current nearly 5.1 million. So that's the big growth in population. So in response to the pressures on the water supply under this the drought condition, the federal government and the state government has been looking at different options. So they have different response to the drought. So this included water conservation. So we've been experiencing the water restrictions, and also looking at desalination, water reuse, stormwater collection. So all households has been encouraged to install the rainwater tank with government's incentives, and also the on-site water reuse are also encouraged. Among this response, the largest response was the 15 billion Australian dollar investment for the seawater desalination and indirect potable water recycling projects. So this included 5 major seawater reverse osmosis desalination plants constructed in 5 mainland state capitals. So later on, I'm going to show you that map. So where are these plants and what are their capacities? So these 5 major desalination plants do not include the second major seawater desalination plant built in WA, Western Australia. And apart from that, we can see 4 potable water recycling plants were constructed and commissioned in Queensland, Brisbane. So this is basically some information about why seawater desalination has been considered by the governments as an effective way to address the drought problem. Today, we have around 270 desalination plants in Australia. And apart from those major plants, most of the other plants are pretty small in scale and used for both seawater and brackish water desalination on a range of different purposes of use. So this map would be provide you some better ideas about the locations of these plants. Australia is considered as the driest continents, one of the driest continents on Earth. Probably many of you had the knowledge that most of populations in Australia spread on the southeast coast and west coast. And that's why you can see all these major plants were built along the coasts. And you can see Melbourne, Sydney, and the Gold Coast of Queensland, and Adelaide is in South Australia, and Western Australia. All these major capital cities in the mainland have the seawater desalination plants, with Melbourne's Victorian desalination plant the largest in capacity. So later on, I'm going to give you more information about the Victorian desalination plant. And this table provides you with more details about these plants. So including the plant's name and the locations, and what's the initial investments, and give you some ideas about the scale of the finance requirement for these projects, and also their capacity, design capacity, and completion years. So just give you an example, what's the main considerations behind the Melbourne's Victorian desalination plant. As many other parts in Australia, Melbourne experienced 13 consecutive years of below average rainfall. And this has resulted in historically low water storage, as you can see from this chart. So this chart is for the water storage data for the Thompson Dam. So Thompson Dam is one of the major freshwater storage dams for Melbourne. And as you can see from 1997 to the 2008 and 9, the less rainfall caused the water storage dropped dramatically and to something around 20%. So that was very risky and it's very alarming. And this triggered government's decision to build the Victorian desalination plant to address the security of water supply for long term. So we know drought has happened before, and we all know it will happen again. So this was behind the decision. A little bit more information about this plant. So this is a snapshot of this desalination plant. Its capacity is 150 gigaliter per year or 450 megaliter per day. It was once the world's second largest plant, following the Israel's Sorry plant, but now it's pretty much out of the top 10 because we have some recent mega plants built in the Middle East. They have much larger capacities. For this plant, it has cost about 4 billion Australian dollars. So you can see it's very expensive project. And with regard to energy consumption, it needs 90 megawatt. In translation, so each day it would consume 2,160 megawatt hour. And my calculation with regard to the specific energy demand is about 4.8 kilowatt hour for 1 cubic meter of water. So this plant also produces about 200 gigaliters of out brine. It needs to be sent back to the ocean. So this is from the water recovery of 40%, right? 60% of the feed is the brine stream has to be sent back to the ocean. This plant has been idle for a number of years because after the commission and all of a sudden Melbourne and Victoria and other parts of Australia got a sufficient rainfalls. So our dams get filled with healthy amount of water. But from 2 years ago, the government started to order the desalinated water from this plant. So last year, the government ordered 125 gigaliters from this plant, and this year the same amount. So these are used to boost our storage dam. And this also actually caused a lot of public and political debate whether this plant, the build of this plant was the right decision. Right? That was because we have experienced sufficient rainfall, and we actually use less of this plant over those years. So that's part of the story. It's like any other emerging options for water supply. So seawater desalination has gained a lot of different views. And there has been a survey conducted by Australian Water Association in combination with Deloitte. So about 1,200 water professionals in different areas got surveyed about their view of the seawater desalination in Australia. As you can see from the survey results, most of the, overwhelmingly, I think 96% of the surveyed people believe that seawater desalination can provide sufficient and safe and reliable drinkable water for our cities, for our communities. There is no doubt it can achieve that. However, if you look at the views about the cost effectiveness and also the sustainability aspects of seawater desalination, they are mixed response. So this highlighted some issues and challenges to seawater desalination in Australia and also around the world. As you can see, the key barriers identified for the implementation of seawater desalination in Australia, including capital and operating costs, very, very expensive, and public perception. This is related to the high energy use and also the potential environment impact because of greenhouse gas emission and some waste streams. So for example, brine. And also after years of use, you will end up with the used membranes, right? How do you deal with those used membranes and the modules? So that's another issue. And in addition, so it seems a bit of lack of transparent assessment of desalination and other supply options, whether desalination is the best option. So there has been some concerns, right? And lastly, so there's a lack of a bit of information sharing among the industry and the general public. So this has been because if you look at the main desalination plants in Australia, they were contracted with different companies. And I think that there is one thing we can understand is those companies would not like to share the critical information because this potentially against their commercial interests and technical advantages. So very quickly, the typical project cycle, like probably other projects, you need to initiate the project and get approvals from the federal environmental minister and also the state planning minister. And then you call contracts and get the contract signed. And then you build and maintain the plant. So this is usually a 4-stage contract type: design, contract, operate, and maintain. With different projects, the contract year be different. So for example, for Sydney desalination plant, it was 20 years with the Veolia group. And for the Perth desalination plant, it's 25 years with the Suez Degremont group. Very quickly, to summarize some lessons or some experience learned from the Australian's journey. So to be resilient for water supply, it's important to consider a portfolio of water sources. Do not just rely on 1 or 2 water resources. So these resources should include something independent of weather and climate, for example, desalination and the wastewater reuse. So we should consider all these options. And we have learned that investment in seawater desalination and water reuse can enable rapid and affordable solutions. Not like other options. If you build a dam, storage dam, it could last for a decade or longer. And desalination and water recycling can deliver very quick results. And very importantly, innovative desalination technologies and renewable energy are the key to address those important economic and sustainability issues. I'm pretty sure Professor Wang will give us a bit more about the current advancements in this area and talking about some innovative ideas. And lastly, we should have a good, robust collaborations between different parties, industry regulators, governments, and the community. So very quickly, by highlighting these challenges, at RMIT, we have different groups working on desalination technology and water reuse. These include the JGA's group and Abjad's group and my group, covering different parts of the desalination and water reuse. And if you want to know more about our activities, you're welcome to contact us. And finally, I think you may want to know a little bit more about how the research and innovation activities in this space got funded in Australia. It's like many other places, the funds usually come from the government. For example, the government have the regular and the specific schemes to support the research and innovations in this space. So this including research hubs, training centers, industry linkage projects, and also we have industry-led research centers. We call that cooperative research centers. So they have different schemes. And also the companies, if they have some issues need to be solved, and then they can provide funds to get some research done to fix their problem. I think that's pretty much all I need to talk, and I'm happy to answer any questions to me, and happy to join the discussion after the presentations. Thank you for your attention.
Thank you, Prof. Fan, for your very informative and interesting talk, which covers actually your experience in Australia, which will be very much useful for us in future. And the discussion we will have at the end of the session. So now let's move to our second speaker of the day. Yes. Okay, now our second speaker of the day is Prof. Wang Rong. She is currently affiliated to the National Technological University, Singapore. She is President's Chair Professor in Civil and Environmental Engineering at NTU and Director, Singapore Membrane Technology Centre, SMTC, Fellow of the Academy of Engineering, Singapore, and she is the founding President of Membrane Society of Singapore. Now, her areas of expertise include novel membrane development for water and wastewater treatment, liquid purification and gas separation, development of novel hybrid membrane systems, and process simulation. So basically, she works in developing membranes. So today, she is going to deliver her talk on development of novel reverse osmosis membranes for water reuse and desalination. Over to you, Prof. Wang.
Thank you. Thank you for your kind introduction. I will share my screen. Can you see my screen?
Yes, we can. Yes.
Okay, let me wait. How can I get is the full screen?
Still
No?
not. No,
No.
I think yes. Yeah.
Then let me see. Since I cannot move. What happened to this one? Sorry. I get a full screen. Okay, let me back to the beginning.
Now that's fine. It's okay.
Right, now is the full screen, right?
Yes.
Okay, I get the laser points. Sorry. No, he's not here. Wait, what's wrong? This should be the, let me, no, how can I get the laser, the points? Give me a moment. Is here?
It should be there.
Then why I cannot find the points? Anyway, I just move my mouse. Seems something wrong here. Yeah, let me try again.
Option. There's a pointer option there.
Pointer option. Pointer option. Okay. Here. Okay. Thank you. That's great. Okay. A very good morning, fellow colleagues, ladies and gentlemen. I'm Rong Wang from Nanyang Technological University of Singapore. It's my great pleasure to attend this webinar organized by the University Paladenia. And I would like to thank Professor Janadashan for the kind invitation. In this presentation, I would like to share with you our work on developing novel reverse osmosis membranes for water reuse and desalination. I think this is a good combination with the first speaker, Professor Fang's overview. Basically, my talk will cover 3 parts. First, I would like to provide some background information about Singapore's water situation and let you know why membrane technology is so important for us. What's the incentive for us to develop the novel membrane technology? Because this is my first time talk to the audience from Sri Lanka. After that, then I will go a little bit details to share with you one of our work on novel membranes, that's biomimetic membranes for water reuse and desalination. Finally, I will wrap up my presentation with conclusions. Let's start from this format. Can you see Singapore? Actually, Singapore is here. You can see here. This Singapore is located in the southern tip of Malay Peninsula, just a small dots. Sri Lanka is here. We are quite close. Singapore indeed is very small, and we have limited space. The mainland of Singapore measures 50 kilometers from east to west, and 34 kilometers from north to south. We are short of the land. We are also short of the water. We are short of the people. We only have 5.5 million population. Our NTU, Nanyang Technology University, is located in the west part of the island. Singapore is short of the resources, but you may not realize that Singapore is ranked top 1 as the most water-stressed country in the world. This data is based on the World Resources Institution provided in 2015. So Singapore indeed is a very water-stressed country. Let me show you a photo. This photo shows water rationing in Singapore in 1960s. We need, have the long queue to collect the water. 50 years later, now if you come to the Singapore, in the downtown, you can see beautiful marina reservoirs here. And we have a highest swimming pool located in the top roof of the landmark building here. Near the Changi Airport, you will see the tallest indoor waterfall. You can see water everywhere, at home, everywhere. You just turn on the tap, you can get clean water. Then you may ask, how these miracles happen? Well, in the past 50 years, Singapore has developed sustainable water supply systems for water supply. One is catchment water from the rainfall. The second is the imported water from Malaysia. The third one is new water. The next one is desalinated water. We have 4 national taps for our water supply. What is new water? New water actually is produced from treated used water that is further purified using advanced membrane technology. You can see the process. There are 2 membrane units here. One is microfiltration, another is reverse osmosis here. Then plus with the UV disinfection, the final, the water we call new water is ultra clean and safe to drink. Now, this photo just show you the new water plants looks like. You can see that's the all membrane modules here. Now we're talking about desalinated water, seawater desalination. We use advanced membrane technology for seawater desalination. Before we talk about the desalination, let me explain the new water capacity. New water currently can meet up to 40% of Singapore current water demand. By future 2060, this number will increase to 55%. That's the new water. Then come to the desalinated water here. We use the RO desalination plant to produce water, to get the water from the seawater. It meets up to 25% of Singapore current water demand. By 2060, this number will increase to 30%. From this number, you can see membranes are very important for Singapore's water supply, right? We use membranes for a new water production. That is to handle wastewater. We call water reclamation. We use the membranes for seawater desalination. That is also using the reverse osmosis membrane technology. But if we use the membrane technology, the current existing technology for water production, by 2060, actually the energy consumption will increase significantly. The energy will be 4 times of current energy value. This imposes a significant challenge to us. So we need to develop highly effective membrane technology for water treatment and water production. How to improve the membrane technologies? We know there are 2 aspects. One is about the system design, that's membrane engineering issue. Another key issue is membrane unit itself. How can we improve the membrane performance in terms of the water permeability? If we can remain the same selectivity, that they can reject the pollutant and the salts. This is one of the review article developed by our group at the Singapore Membrane Technology Center. A lot of innovations has occurred in the past 20 years. People think about how we enhance the water permeability of the RO membranes. Later, I will further elaborate this part. In addition to the R&D in the laboratory, actually the funding agency like PUB, Singapore National Water Agency, call for technology translation for those groundbreaking discovery. Laboratory study is not sufficient. You know, a lot of funding resources go into the water and the membrane domain. We get a new technology, new invention, but publication in paper, that is not enough. The key aspect, another key aspect is the scale up and the translation of these discoveries so they can put it into operational practice. This is the guideline from the Singapore government, the funding agency. It means the laboratory study in the TRL level 1, 2, 3 is not sufficient. That's the normal technology readiness level for the laboratory study. We need further to scale up, to push the technology to the higher level. Then industrial can adopt our technology for real application for commercialization. Bear this in mind. Now, I would like to share with you what we have done to develop the one type of the reverse osmosis membrane technology. We start from the laboratory and go through the scale up and push for the commercialization. That's the nearly 12 years efforts for one type of the project. We know there are various types of the pressure-driven membrane process: MF, microfiltration, ultrafiltration, nanofiltration, and the reverse osmosis. MF-UF are normally used to remove the particles, big molecules of the organic molecules. And the nanofiltration have a smaller pore size. It can be used to reject the divalent ions like the calcium, magnesium, and remove the natural organic matters. These natural organic matter have a smaller molecular weight. Finally, we use the reverse osmosis RO membranes to reject the monovalent ions, sodium chloride, only allow the water to go through. So in terms of pore size, you can see here, the RO membranes is considered as a dense membranes because of it's very dense. So we need to have to apply the high pressure to run the filtration go through the RO membranes. The state of the art of RO membrane is the thin film composite RO membranes. That's the typical SEM to show the structure. You can see there are these parts at the bottom parts is considered substrate support microporous membranes made by the polysulfone typically. Then on the top, there's a thin layer, polyamide layer. Actually, this is the selective layer to do the separation. And the polyamide was formed through the interfacial polymerization between two reagents, MPD and the TMC. That's a chemical reaction immediately. Then we get this thin film. This film is very dense to reject the monovalent ions. As a result, actually, the water permeability is very low. Very low. Then to improve the membrane performance, we need to think about the innovation ways to enhance the water transportation through this thin film. Okay, around 15 years ago, people are fascinated with aquaporin. Aquaporin are the natural water channel proteins. Aquaporin was discovered by Professor Peter Agrey, who won a Nobel Prize in Chemistry in 2003 because of this discovery. Aquaporin are highly permeable to water, but highly retentive to the solid. So people think about, can we incorporate aquaporin water channel into the thin film to enhance the water transportation? This is the schematic diagram, like show the thin film. If you go back, it's like this. This is the layer, polyamide layer, thin layer here. So how can we incorporate this aquaporin water channel into the thin film? So this is a big challenge, also very interesting topic. My group at the Singapore Membrane Technology Center in Singapore is one of the pioneers step into this area to work out these biomimetic membranes. You can see the project list. We get the first project in 2009. After project finished, immediately we get another project from PUB, Singapore Water Agency, in 2013. Then continues to get another government agency support, 2014. Then once finished, we get another project, 2018 and 2019. Then you may ask, I believe you are wondering what you have done. Why the government continue pour the funding to this topic for you to do the work? Let me explain to you. Our first project is to prove the concept, develop the prototype, how to incorporate the aquaporin into the thin film. We developed the formula to basically we use the lipid to embed the aquaporin to form the proton lipsome. The vesicles then were embedded into the thin film when we conduct interfacial polymerization. We have two chemical reagents. When they have the reaction, we already put this vesicle inside the matrix. That's when they form the matrix, the vesicle already embedded inside. This work was published in 2012 with 5 patents because we see the aquaporin-based flat sheet membrane can enhance the water permeability by 50% compared with the control without the aquaporin vesicle. This is a very encouraging result. Then we further optimize the formula and work in hollow fibers. We developed the first aquaporin-based hollow fiber membranes in 2015. And the performance, you can see here, increased by 100%, double the water permeability, but they remained a very good salt rejection. When we published this work, actually a lot of the inquiries, people have a question. If this membrane can be, they ask if this membrane can be used for real application. In the real situation, what happened? So we use the real field water, that's from the new water plant, wastewater reclamation plant, we get the field water to do the filtration. Compared with the commercial membrane BW30, the three pieces of the coupon membranes was put in the same setup, run in parallel, the same condition to achieve 20 LMH water flux. But our membranes only need 5 to 6 bar pressure, and the commercial membranes need around the 10 bar pressure. And this operation lasts non-stop for 700 days, nearly 2 years data. It gives us confidence this membrane work. We also test our hollow fiber biomimetic membranes. This is also nearly 1 year testing, 350 days, using the real feed from the new water plant. We also run 20 LMH water flux, but the operating pressure only like the 4 to 5 bar. And then the salt rejection, very good, very stable performance. So all these results in the laboratory study confirm the success of our biomimetic membranes. Naturally, next step, how can we make it bigger? In the laboratory study, in the beginning, it's a very small piece of the coupon, then small piece of the membrane module. Then in 2018, we get a new project from the government to scale up the fabrication of these biomimetic membranes. From the small module, come to the 1 meter long module, like the 500 piece of the fiber, 1,000 piece of the fiber, and finally that's a 4-inch module, 3,200 piece of the fiber. Our latest data I did not put here is the 8-inch module, commercial 8-inch module, contain 12,800 piece of 12,800 piece of the fibers. That's for the 8-inch module, same as the commercial 8-inch module, the size. And you can see the water permeability is over 6 LMH per bar, and the salt rejection is over this 96, the best one, and we have better ones over 96, stabilized that one. For your information, current RO membrane, commercial membranes for brackish water application, the water permeability is the best one, is around 3 LMH per bar with the similar salt rejection. Okay, just show you the facility we have to do the mass production of the hollow fiber membranes and to do the coating layer interfacial polymerization. And here is the test setup. You can see here, that's the test setup. And we built our systems for the testing. At the same time, we never stop for the new innovation and the new invention. In this project, at the same time, we also identify one type of the biomolecules without aquaporin that can adjust the matrix of the selective layer. And I hope you can see the morphology here. This is the top layer of the morphology cross-section with these spatial biomolecules. At the top one is without the biomolecule. You can see big difference. Actually, these molecules can adjust the control the matrix of the selective layer. So we call it bioprogrammable membranes, aquaporin free. And it's amazing, this type of the membranes have similar performance as aquaporin-based membranes. You look at this water permeability and the salt rejection, very similar result. This type of the membranes, because we don't use aquaporin, make it more cost-effective and much simple for the fabrication. So by far, we have two types of the biomimetic membranes. We do the on-site testing, pilot testing in the new water plant. The photo shows the container inside. You see the 4-member module here. 2 are the biomimetic with aquaporin, and another 2 is the bioprogrammable membranes without aquaporin. But also 2 types of the membranes show exact same performance for the real testing. The testing already lasts for 100 days. The setup still in the PUB plant. The testing is ongoing. We plan to test for at least a half year to see the real situation, because you see here, the real water from the plant goes to the piping, come to the container, big container, then we go to our member module, then goes to these 2 containers and discharge the water tank and go for the discharge. This is 14 cubic meter per day, the capacity we are running currently on site. After this, 6 months later, we will build 100 cubic meter per day capacity, another big pilot testing on site to further demonstrate the applicability for real application of our biomimetic membranes. With this, I'd like to make a conclusion. The growth of membrane technology is assured due to the impending water scarcity. And we have successfully developed novel biomimetic membranes, all membranes for water reuse and desalination. And it is important to improve the technology readiness level for technology translation. As a researcher for the technology development, I believe the commercialization of advanced membrane technology should be the ultimate goal of the membrane research. Before I end my presentation, I'd like to thank my team, my staff, my students, my collaborator for their dedicated work. They worked with me over the past 10 years just for one topic. And the significant funding support from the government. I'm very, very grateful for the strong support for the funding agency. I would also like to thank the Singapore Economic Development Board for funding support provided to Singapore Membrane Technology Center. We have world-class laboratory at SMTC, so that can support us to do the research. Okay, I think this is the last one. With this presentation, I would like to thank your attention. I'm happy to answer your question in the discussion later. I'm looking forward to collaboration with all of you if we can find mutual interest. Thank you very much.
Thank you very much, Prof. Wang. Actually, your presentation is very impressive because it clearly shows us how we can, continue our laboratory work to the actual grounds. So now, with that,
sorry,
yeah.
I can stop sharing, right?
Yes.
Okay, yeah, that's clear. Okay.
Now it is the time for our panel discussion. So for the panel discussion, we have Prof. Wang and Prof. Fan with us. And in addition to that, we have 2 additional panel members, Professor Jega Jagadisan and Dr. S.K. Veragoda. Now, before start, let me introduce Prof. Jega and Dr. Veragoda to you. Prof. Jega Jagadisan is a professor of environmental engineering and the director of Water Effective Technologies and Tools, a WET Research Center at RMIT University, Melbourne, Australia. And he is the editor-in-chief of several journals and also the secretary of Stormwater Quality Improvement Device Evaluation Protocol, Governance Panel of Stormwater Australia, and a consultant of Yixing Environmental Protection in Industry Development, Yixing City, China. And our next panel member is Dr. S.K. Veragoda. He is specialized in water and used water treatment, and he is currently serving as the project director of China Sri Lanka Research Grant Project attached to the Ministry of Water Supply Sri Lanka. He leads the team attached to the Water Safety Plan Advisory Unit in the National Water Supply and Drainage Board. In addition, he has been recognized as an expert on application of WSPs and international auditor in the region by the WHO. And he also serves as a visiting lecturer in many national universities, including our University of Peradeniya. So with that brief introduction, let's move to the panel discussion. Now, first, since we already actually listened to stories from Australia and Singapore, I would like to ask Dr. Veragoda to brief the Sri Lankan condition of use of membranes for water treatment.
Thank you, Dr. Nadishani, and very good morning and good evening to everyone. And I mean, I like to get a sort of introduction about the membrane usage in Sri Lankan context. So actually, we were not that keen in desalination because we in Sri Lanka, we get around 2000 millimeter annual rainfall, almost like all the parts of the country. So, but with the climate change in last 10 years, we find that we are heavily affected and we are getting long dry spells. And country having the plan, the government, the president of Sri Lanka has declared that by 2025, we have to move to 100% safe water coverage in the whole island. So in that terms, we have to go and see how that we have to cover up the dry zone, which is being heavily affected by the climate change. So that in that scenario, we would see some options like in northern part of the country to come up with some alternative, like there's no other choice, either going for groundwater or ocean water, that's desalination. So we are in the process of putting up the first treatment plant in largest scale in the country of 24,000 cubic meter capacity per day. And all the groundwork has been done, and now is to turn into the construction of the facility that is almost at the last stage and is coming under the funding of ADB. And apart from that, we have some small scale experiences in northern islands like Delft. We were running a plant almost like of 3-4 years now in the capacity of 200 to 300 cubic meter. That's not that big level. So when we are getting into the inland water, so we are going with RO, we are going with nanofiltration in small scale, like 25 to maybe like maximum 50 cubic meter. That's for groundwater treatment, not for desalination. That is a very brief note on the application of membranes in Sri Lanka, Dr. Nadishani.
Yes, thank you, Dr. Veragoda. Now, yeah, Prof. Jega, now we would like to hear actually your experience in membrane related research in your laboratories, because I have seen Prof. Fan and you work together in your center. Yes.
Maybe, yeah, I can say a few things based on speeches here. So it very clearly we can see there are several topics in desalination that need kind of continuous discussions and also the industry participation. Then we can actually extend the existing knowledge to the implementation. So we could clearly see that from Professor Rong Wang's speech. So how that laboratory scale can be implemented. To do that, we really need the industry participation. And the topics actually we always see in desalination is like Dr. Veragoda mentioned, that whether we can rather utilize nanofiltration instead of RO, and whether we can use it alone or in conjunction with RO. That is one thing we are interested. And also the managing concentrate. Actually, that's a big issue from small, medium, and large scale plants. How are we going to manage the concentrate? We do some calculations. It tells sometimes very large plant, if you recover the salt, that is very beneficial, but not every large plant can recover the salt, because maybe the way they get their energy, that doesn't help them to get a cost-effective salt recovery. And also that improve the water recovery, you will see Professor Fan mentioned, still we are having only 40% recovery. And then Professor Rongwang mentioned she can improve the water recovery through that novel improvements. And energy recovery, there are a lot of energy recovery systems there, but the implementation is lacking. So the water recovery and the energy recovery, there are a lot of knowledge is existing, but the implementation is lacking. That's where the industry should join with us so that we can implement them. And then it also will lead to the innovation. So these are the things we are looking into. So in our laboratory, what we are trying to do is whether we really come up with some very clear plan for the concentrate management for different scales of plants. Small scale plant, what are the really best solution you have for salt recovery or the concentrate management? So that one thing we are doing. And also we are trying to see whether we really clearly develop a plan to recover salts. Although there are a lot of theory available, it is not really in practice people are utilizing. So these are the activities we are doing in our laboratory. Thank you, Nadishan.
Yeah. Thank you, Prof. Jega. And now, yeah, if I go back to Prof. Wang. Yeah, Prof. Wang, now you have achieved higher recoveries because I think in our small scale plants in Sri Lanka also, we have noticed the recovery is always below 50%. And the bad thing is we pump out groundwater and we probably wasting half of that. So it is not for seawater. Now, in that context, can you further elaborate on this increase of your, the recovery through development of membranes?
Yeah, thank you. Thank you for the good question. Actually, using the RO for remove the monovalent ions, actually there are two types of the water. One is brackish water, as you see the webinar's topic is about the brackish water and the seawater, right? Brackish water actually salt concentration is not very high. And then for the seawater, then the osmotic pressure because of salt concentration in the seawater is high. There are two types of the RO membrane basically, So these two types of the membranes actually their permeability are different. We need to choose the right membranes to do the salt removal. So that is for the monovalent, the sodium chloride removal, brackish water or seawater. Totally two types of the membranes. In the market, you can see BWRO and SWRO. That's two types different. What I mentioned in my presentation, I give the result for the new water. Actually, that's for like the brackish water. The salt concentration is low. You can see like the 1000s ppm, 2000s ppm, this type. And for our brackish water, the new water, our recovery in the new water plant is 70 to 75%. And we need to have these membranes to have a high permeability. This is the key. the high permeability, then you can recover more water, right? You mentioned about like around the 50% recovery or below that one. So the key is to, you need to have good membranes, have a high water permeability. The second, you need to choose the right membranes to use. Professor Jaga mentioned about, they prefer using the NF. That depends on your target removal. If use the NF, you want to remove the divalent ions. If your water contains the magnesium, calcium, you want to remove the divalent ions, you use the NF nanofiltration. And actually, in my lab, I have another new invention. That's low pressure hollow fiber NF membranes, and the flux much higher than the commercial membranes NF, and only 2 bar pressure can operate. So that's my comments. You need to choose the right membranes for target the removal. That's the key.
Yeah.
Okay.
Yeah. Thank you, Prof. Wang. Now there is a question from the audience to Prof. Fan actually. Now this is related to the brine disposal into the sea. Now the question is how sustainable or how good to dispose the brine into the sea, and what are the problems, environmental issues we might see by doing so?
I think that's a good question. And at the beginning of the application, can you hear me?
Yes, we can. Yes.
Yeah. Okay. Yeah, I was not sure because of the microphone icon. It's yours actually. Yes, at the beginning of the application of the seawater desalination, actually there has been a lot of concerns about this practice because you have to send back to the brines to the ocean. Over the last perhaps 20 years or 10 years, recent 10 years, I have heard initially, 20 years ago, there are some research already conducted. And by that time, the conclusion was there was no evidence that, you sent back to the brine will cause any, noticeable issue to the ecosystem. But over the last 10 years, there are some other research actually concluded that probably the previous conclusion may be underestimating the long-term impact to the ecosystem, the marine system. That's why in my presentation, I have outlined one of the things is the long-term impact should be better understood, right? So that is one thing. And there are a lot of things we don't know yet because unfortunately you have to provide evidence, but evidence may not be immediately available. So it needs probably years of research. Another consideration is as JGA and other groups working on the resource recovery and also the reuse of the brine. And the main purpose for that is reduce the volume and recover useful components. In the meantime, you actually reduce the salt level. At the moment, you may not be able to achieve zero liquid discharge, but at least you are largely reduced volume of the brine. And then you could, eventually make that safer in the form to return to the ocean. So my comment basically is now we need to rethink about the brine discharge to the ocean practice based on the recent research that previous conclusions underestimating the long-term impact. So I don't know whether this is sufficient to answer this question.
Yeah, yes. Yeah, thank you, Prof. Fan. I think he answered it very clearly. Now, there is actually one additional question coming back to Prof. Wang, because Now it is actually raised by actually one of the participants. Now, when it comes to our Sri Lankan groundwater, the major, we have two main issues actually. One of them is hardness, that is calcium and magnesium. And the second thing is fluoride, so which is a monovalent ion. So one of our major issues is actually when, I mean, using NF, we might, go for higher recovery, but then our fluoride might having issues removing fluorides. So,
that's a very good question. Basically, you cannot rely on just one unit to do the job, to solve all your problems. So actually, in a lot of systems, several units, like there's a combination. For example, you can use some unit as a pre-treatment, and then you do the job. Combination will be the solution. For example, you have the calcium, magnesium, you need, that's hard water. You need to remove the hardness. Then you can use the first stage to use the low pressure, the high flux, the nanofiltration. That will work, remove your calcium, magnesium from the water. Then you can use another second stage, like the RO, to do the job. That's your concern. You have the monovalent floral elements there. You can remove that. I think let's think about it. That's like the process optimization. You cannot just rely on one unit. You say, okay, I use the RO. The one stone killed all the birds, but you should know they will foul the membranes. The membrane will not work for long. Immediately they will be fouled. All the foulant will reject. So that's why normally, even for the seawater desalination, we have used the UF to do the pre-treatment to remove those foulant first. Then we go to the RO unit. So that's my suggestion.
Yeah, thank you. Yeah. So now actually another question which I would like to direct to Prof. Fan is, now how about cost of cubic meter of water in terms of the charge we can, I mean, the cost of water, RO treated water compared to other technologies, maybe let's say conventional water treatment process?
Yeah, that's a very good question. And it's always cost and energy consumption, the most debatable thing in this kind of technologies. I'd just like to provide a general comment with regards to the energy consumption and the cost trend. So we have seen that the membrane technology has largely reduced the energy consumption. I mean, since the year 2000, and then the membrane-based, especially RO technologies, actually dominant market. I mean, to now it's basically most. I mean, I can't say all, but almost, all of the new plants are actually the membrane-based or RO-based. So we have seen the energy consumption of the thermal plants from my number. It has been pretty high, so it's over 10 kilowatt hour per cubic meter. And we have big improvement for the membrane process from, the beginning, a little bit lower than that, probably 7 or 8, and then gradually reduced to 4 to 6 over the time Australians, the major seawater desalination plants were built and operated. To now, I think there are some recent new plants in Middle East, especially in Saudi Arabia. Some data showed they could make the energy consumption much lower. So to now, I think it's something around 3 kilowatt hour per cubic meter can be achievable, but it depends on the situation. I'm not saying it's applied to all, but that is achievable. This including about 2 kilowatts per hour on the RO process alone. And also you're looking at the intake and the pre-treatment and post the treatment and the distribution. There will be more added on the two. But with the improvement of new technologies like Professor Wang's group work, so their membranes can work at much lower pressure compared with the some other commercially available membranes. So these are very encouraging. And in terms of the cost, and also some new plants suggest they can achieve under about 50 cents, US cents per cubic meter. So some new plants like those Yanbu and Jabal plants in Saudi Arabia, so reported, so that's under 50 US cents per cubic meter. And again, and if you can lower the energy consumption and you can make the module cheaper, and then that will further reduce the cost. So I don't know if I have answered that question.
Yes, yeah. Thank you. Now, Dr. Verakoda, in that, if we come to that number, 50 US cents per cubic meter. So if we compare with the current waterboard 1 cubic meter, yeah. So can you comment on that? Probably.
Yeah, there are a lot of actually factors affecting the cost depending on your finance arrangement, depending on your scale. If it's smaller scale, probably would be more expensive. So it's depending on a lot of things. So you have to be very careful, when you compare with the cost.
Okay.
Yes, Dr. Nadishani. So that's something, we are struggling to put up this RO as an advanced technology in the country, because right now, so you find two cost figures when we are taking up these financial figures here. One is the price at your doorstep, because in addition to the production cost, you have to keep on pumping this energy. Additional pumping cost is coming, especially country like Sri Lanka, this hilly area, we have a lot of energy consumption for pumping as well. So if we just count the production cost at the doorstep, it's around, including pumping, it's around 0.25 US dollar cent, 25 cents US dollars. That's in Sri Lankan currency, is about 50 rupees. So when you take up the production cost in the conventional treatment, it's almost 1/5 of that. So that is around 10 to 15 rupees per cubic meter. That's Sri Lankan prices. So when we go with the financial calculation and the operational cost recovery in this proposed RO plant in Jaffna, is almost coming like about 80 cents of US dollars. That is how it's coming. So that's really because this is the first time and the technology is coming not from Sri Lanka, and our energy price is a little bit probably maybe higher than of course Middle East, and because we are relying on thermal energy and coal power to a certain level, so that's prices also added, as Professor Fan said very correctly. So when it is coming to the Sri Lankan context as a developing country, how the sustainability, are we going to go for water supply treatment plan, the water supply scheme based like tariff system, or are we going to have a generalized tariff system for the whole country? That's a question that we are thinking right now to see and go ahead with this expansion of this RO technology in country desalination.
May I add something to that?
Yes, Prof. Jagger.
There is we discussed this in our first webinar, but for the benefit of the the participants today, I would like to say this one. Even a very large RO plant, for example, 25,000 cubic meter per day feed, right? So there are three things we can do. One is actually you have a high pressure you need to overcome the osmotic pressure. So, but the pressure will be retained in the concentrate. So you recover the pressure, so the energy recovery. That is, there are a lot of devices there already, that you do. Second is, if possible, you recover the salt from the concentrate. The third is what you do is you add a nanofiltration in the front as a pre-treatment, and also you use membrane distillation coupled with the crystallizer to do the salt recovery. Then suddenly the entire system, maybe your capital cost will increase, but suddenly the entire system will give you more than 90% of your water recovery, and then you produce salt. So the value of the salt is much more than your operating cost. So if you combine everything, actually this plant will give you money. For example, every cubic meter of water you produce, you will make around 40 cents US dollar, right? So that is the theory. But in practice, that is not happening. So that's where we should go forward. So slowly, maybe energy recovery you do first, maybe then you try to do salt recovery, then you combine all the systems together, and then you produce water. And obviously that water recovery can be improved by novel membranes. Now we have a very high pressure RO membranes. It generally takes 50 bar. I think now they are going up to 150 bar. Professor Rong Wang can tell exactly what can happen for the RO membranes for seawater. So those are the things we can do actually to improve. But somehow there is a lag in the research and the translation. Maybe there are a lot of cost involved, and then you have to prove. You can see every test in Professor Rong Wang's group, they do for several years to make sure it is demonstrable. So those kind of things we actually have to work. So that is the stage we are in, I think, in desalination. In Middle East, they do a lot of work. So I think that's the place they are exploring all these kind of activities.
Yeah, now further to that, there is one comment given by the participants, one of the participants. Now, if we think of using renewable energy, so if there is any, day, let's say, where we cannot obtain what we need from the source, so how about the sustainability of the process?
So is this question to me or to who?
Yes, Prof. Fan.
Yeah, all right. I actually raised that innovative technologies and renewable energies are two key considerations to address the sustainable issues. So I think definitely using more renewable energy will definitely minimize the potential environment impact with regards to, for example, greenhouse gas emissions. If our plant using the fossil fuel powered electricity power, that's definitely help. I just give an example that in Perth, WA, so that was the first major desalination plant in Australia. So the energy requirement for that plant was 24 megawatt. And they actually used all the renewable energy from a wind farm. A wind farm can produce 86 megawatts electricity. So that's more than sufficient for the powering that desalination plant in Perth. So this is an example that we could actually use wind energy, right? And then this is to reduce the emissions. However, I can understand that some arguments with that, the desalination plant itself is energy intensive, right? So you actually you use the renewable energy from there, but that renewable energy could be supplied to somewhere else. I mean, there was, I don't know if you understand the point. So, I mean, that is one thing. But in my view, I think definitely using more renewable energy will actually increase the sustainability overall, because this is the market, right? Renewable energy market, if the RO plant use that energy, so that means there's a market there, right? So this will produce the investment in the renewable energy sector. So that is one hand, but I cannot say that is the only way you can achieve sustainability for the desalination practice. But that is one important way we can improve.
Okay, thanks for that explanation. The last question, I think Prof. Jega or Dr. Veragoda can answer probably. Now, there is a huge concern related to remineralization. So, after the RO treatment, so what would be the best practice?
Yeah, I think I can tell from our side, but Dr. Veragoda might be telling from his practical point of view. Normally what you do is there are many ways to remineralize. Sometimes you bypass certain amount of your seawater, and some you treat. There are several passes. So you can, after some pass, still you will have certain amount of minerals. So that you allow to mix them with the finally treated water. That is one way to do. Or you remineralize with after treating everything. So there are many ways to do that. So it is depending on the manufacturers and the users, they will use differently. Yeah, maybe we can hear how the systems in Sri Lanka they are utilizing. Maybe Veragoda can tell us.
Yes, Professor Jega. I mean, like, so when it is coming to Sri Lankan context, we are talking about the groundwater treatment. So as previously also said, so we struggle with hardness and we get in fluoride and maybe certain level of nitrate and it's like manganese and so on. So that's so when you take up, I mean, like, so when it is coming for the groundwater, the question that we are all the way that discussing with the medical experts also, that how much is required for us to go with remineralization, because we are getting food minerals through food as well. All our the meals getting sort of certain amount, but I mean what I do find, like, I mean, there's a knowledge gap. It's still, I don't know how far that world has gone in this way, but in Sri Lankan context we are still thinking of this. So there are a couple of publications done recently with the low income groups, especially not for the people who are having a really, I mean, like certain the rich and moderate community can manage with their food inputs, but when it's going to come in the low income, they are struggling with this. This is what we do understand. So I mean, like in Sri Lanka, I mean, like what we do think of, like, I mean, Professor, so if we can, because we got our standards, international as local standards, so what we are thinking is that partly we are treating water, I mean, like we can bypass some, as you said, like, so then we can blend back the treated water and partially treated water, and we can bring up the mineral content which is to suit the drinking water condition requirement. So other than that, I mean, like they are doing with the standard processes of remineralization as well, but frankly speaking, this is not done in a proper manner, like, so that is something that we are struggling. So that's to be educated, that people should be aware about this requirement. So that is what the condition in the country.
Yeah. Yes, thank you. Now, unfortunately, we have to wind up the session now. And there are many other questions. I think the participants, please, you can actually send your questions to Prof. Wang, Prof. Fan, or Prof. Jega, or Dr. Veragoda through email. Okay, now, before winding up, I would like to thank our distinguished speakers, panel members, and organizers of the webinar for providing this platform for us. And also let me thank all the participants to make this event a success. And I think I have to introduce the next webinar as well. Yes. Now, the next webinar, webinar number 4 of this series is going to be on cleaner production and zero liquid discharge concepts for industry. We have two speakers, Associate Prof. Abhijit Det, Associate Professor, Mechanical and Automotive Engineering, School of Engineering, RMIT University, Australia, and Dr. Asela Kulatunga, Senior Lecturer, Department of Manufacturing and Industrial Engineering, Faculty of Engineering, University of Peradeniya. The session will be moderated by Professor Parakrama Karunaratne of Department of Chemical and Process Engineering, University of Peradeniya, Sri Lanka. Okay. With that note, I would like to wind up this session and have a nice day. Thank you so much.
Thank you.
Thank you.
Thank you very
everybody.
much. Thank you.
Thank you,
Thank you so
Professor.
much.
Yeah, bye-bye.
Bye.
Bye.
Thanks.